Okay, we are all already answered that the right one is better. True? Here's the dealio. The right one is better. I totally agree. The reason it's better is because it's good for back substituting, and it actually has a name, row echelon form. It's called a stair-step pattern with a leading coefficient of 1. A stair-step pattern with a leading coefficient of 1. A computer program would be told or instructed or programmed to do in some senses when simplifying a matrix. Now, we haven't really done matrices. Don't worry, that's really more like chapter 8. However, it's not always going to look easier to some of you. Some of you would be like, oh, hey, look, I can just add these two together. Yay, and I can cancel out the x's. Well, that's good and all. You're not wrong. But it's not following the system that we're going to learn, number one. It's not following the system, number one. And number two, are you really that much closer to a solution? Because you still have y's and you still have z's, and you only have, if you put these two together, you only have one equation. One equation, two unknowns. Is that good or is that bad? It's bad. What we want is we want to know one variable, and then we want to be able to plug it in to find the other variable, and then plug both of those in to find the third variable. Oh, that's beautiful, but that took some work. Rarely ever will the problem start off like this. Usually we go from something like this, following a system, trying to get it to look like that, so then we can go ahead and solve and finish. So, what's going on? Kim, notes are up. Here you go. What's going on? We have a lot of notes to take. We're going to be going pretty quickly. Here's something new called Gaussian elimination. Gauss was a mathematician. A long time ago. Smart dude, did a lot of stuff. Not just having to do with this. Row operations. If you guys were to go into your calculator, if you were to go into the matrices and go into the matrix math menu, you would see different things having to do with row swap, R1 plus R2, row addition, row subtraction, row multiplication. You would see a lot of different things with the word row. Matrices work by rows. Rows include equations. Hey kiddos, do these steps 1, 2, and 3 look similar to you in any way, shape, or form? Yeah, because they were also the steps or the system for elimination, what was legal. They're also going to be our steps to Gaussian elimination, the legal math for keeping the systems equivalent. I call it the chain game to get to the stair-step system, or the chain game to get to row echelon form. How effective is a chain if a link is broken? So in order to get to row echelon form, in order to get to what you just saw, would be so much easier to get x and y and z with. To get there, and to get there in a systematic approach where all of our work will match, aka we're all doing the exact same system, aka we could tell a computer exactly what to do every time. We're going to have to go link by link, step by step through the process. And if it breaks down in any place, number one, you're going to have work that's different than everybody else's. So if you make a mistake, we're not going to know it, and you're going to have to find it on your own, which is a little bit annoying. Is my sound on? Lo siento. Your work's not going to match everyone else's. So if you make a mistake, it's going to be really hard to find it, and we're not going to have time, long story short, we're not going to have time to basically check everyone's individual way of doing it. So that's not going to be good. And number two, if you don't follow our chain game to the row echelon form, if you don't follow our system, you're not thinking in a way of, oh, hey, a computer could be told to do this every single time, because it's not creative. It's not able to just make new solving procedures every single time it sees a new individual problem or unique problem. Okay, this shouldn't take long to write down because, to be honest, 1, 2, and 3, they're pretty basic. You can switch up two equations. You can multiply an equation by a non-zero constant. You can add a multiple of one to another. That's just legal elimination-y stuff. So let's figure out how to put this all together. And what is our process to getting that nice system that is so much easier to solve? All right, so let's start with the nasty one. Let's start with the nasty one. Here's the system. If I were you, I would get two colors out. If I were you, I would get two colors out. One color can be the system that we're doing, and then another color can be the math. Or the pencil could be the math, and maybe the colored pen can be the system that we're doing. Okay? Now, you guys aren't computers, so I'm not going to make you totally do it like a computer right now. I'm going to let you have a little bit of creativity, but only enough so that we're still all going through the exact same system. So I'm going to go ahead and name these R1, R2, and R3. That would be like if you were typing it, but to be honest, since I'm not typing it, can I use subscripts? Is that okay? R sub 1, R sub 2, R sub 3. What does R stand for? Anybody know? Row. Good. Row 1, row 2, row 3. Here's my system. We are going to eliminate the first variable using R1 and R2 and using R2 and R3. First step, we're going to eliminate. I mean, it's technically two steps. But we're going to eliminate the x variables entirely. First, using R1, R2 elimination, and then using R2 and R3 elimination. So if we were using R1 and R2, kiddos, now it's time for you to be creative. How can I get rid of the x using R1, R2? It's as simple as adding. Sweet. So let's go ahead and do x minus 2y plus 3z equals 9. Remember, if you learned how to work a computer, you could actually have these be like little inputs and have the computer do all the work for you. As far as, hey, take the A coefficient and the B coefficient and then add them, and the C and the D and the E and the F and the G and the H. Anyway. What happens if we get rid? Don't we end up with y plus 3z equals 5? You guys agree? Sweet. We're halfway through our objective. But we also need to get rid of the x variable with R2 and R3. So, time to pull out your creativity math cap. What am I going to do? Good. We're going to go, okay, so we're going to do negative 2 times R. No, just 2, right? Just 2. Positive 6y equals negative 8. If you want, it might be a wise idea to leave that space for the z. And then R3. Now, some of you are like, I would not have gone about it this way. I know that. We're trying to learn the system, building up to the programming behind all the matrix stuff that's in your calculator. Remember, 5 by 5, 6 by 6s. You don't want to do that by hand. Ugh. This is just a 3 by 3, 3 equations, 3 unknowns. What happens? Good. Y plus 5z equals positive 9, right? What do you notice about what I have now that I have eliminated the x variables from the R1, R2 system and the R2, R3 system? What do I have remaining? 2 equations, 2 unknowns. Isn't that like section 7.2? 2 equations, 2 unknowns. What's my system going to say? Now it's time to eliminate the y variable using neither of these or any of those, right? So let's call it R4 and R5. Sound good? Using R4 and R5. Bless you, bless you. Using R4 and R5. Do you guys see what I mean? And put on your thinking caps and be creative. Can we just add down? R4 plus R5, is that going to cancel out the y's? I can keep the R4, but if I keep the R4 this way, what do I need to do to R5? Multiply everything by a negative 1. So negative times the y, a negative times the 5z, the negative times the 9. Remember, we're allowed to multiply everything by something, and the reason I multiply it by a negative is what do I want to happen when I add down? Elimination. Good. There goes that y. And I have negative 2z equals negative 4. Now what? Solve for z. If you follow the system every single time, if this is a consistent system with finitely many solutions, you will have your z after steps 1, 2, and 3. Z is equal to 2. Now check it. If they wanted row echelon form, I know, the purpose is to solve, but hold on. If they wanted row echelon form, the new vocab word we saw at the beginning of the section, do we have it? Kim, you have the example down, right?
Yeah.
Okay. And you followed our system exactly? Cool, let me see. So, row echelon form, what do we got? Oh, no, you don't. Pay attention. You might have the solution, but it's not our system. Row echelon form. Guys, look back at the very beginning of notes. What was the first thing? The first equation, right? What was the second thing? We have the first equation, then we have the first equation, and then we have the row echelon form. Be careful, there's going to be true and false questions with row echelon form. We need an x with a single coefficient of 1. So our system says, take the first one, then take the first 2 and R3, and then take the last one. Do you guys see where this came from?
So we have to make R4.
That would be my advice. Now, technically, Adam, remember, we're not computers. So could it still be row echelon form and have used this one? Yeah, because it would also have a 1 in front, right? But what if we had had this, and what if we had had something like 2 in front instead? And this one had like a 3 in front. Could we have put either one technically to be in row echelon form here? No. So you would have had to divide everything by 2 or divide everything by 3. So technically, row echelon form says leading coefficients of 1. So we're going to use these equations, but we can't always just steal it. I wanted to say that. And technically, you could use either one. But if you're trying to make it match the back of the book, you're going to have to follow the system. And the system says choose the first, choose the last. We got it. Now, was that the final solution? No. And Kim, I think you did get it right. Double check. I think you're fine. In that, I'm coming back to you, Austin. To finish the problem, we're trying to find x and y, and whoa, it's a 3-coordinate system because we're 3D, not 2D anymore. So not just x and y, but x and y and z. Don't we already know z? How can we find y? It's as easy as back substitute. Y plus 6 equals 5, so doesn't y equal -1? Then can't we go ahead and take the 2 and plug them in the z spot, and then go ahead and take the, hey, now we know y equals -1, and plug that in the y spot? X plus 2 plus 6, does x equal 1? Cool. That is the final solution, and that's good, but remember, we're trying to get closer and closer to computer programming, and to do that, we have to do this in a systematic approach that will work every single time. And every single time, as long as this is a consistent system, we can take R1, R2, and do elimination. Now, I didn't make you a computer. We just got to look at it and figure out how elimination could work. A computer, we'd have to go one step further. Then we take R2, R3. We get to be creative, make elimination work. Then we get to take R4, R5, make elimination work. We get to kind of be creative. The step to jump to a computer, you'd have to figure out, wait a minute, how can we make it eliminate every single time regardless of the numbers that are there? But that's a problem for another day. 3 dimensions. What do our vocab terms mean in the 3rd dimension? My artists, now you can have some fun. My non-artists, just use words to say what you see. My artists, you can have some fun. My non-artists, well, you can use words to say what you see. Types of solutions. We have consistent and inconsistent. Consistent, remember? Uh-oh. Uh-oh. Consistent. Didn't I say finitely many solutions? Does anybody see a dilemma with that? This one down here technically could be called equivalent. Why could this one be called equivalent? Can you guys figure it out? It's all the same plane. So equation 1, equation 2, equation 3 would be the exact same surface, the exact same area. So equivalent, they're all the same. Do they look the same? They're probably all multiples of each other, but they're all the same. Consistent, basically, solutions exist. So maybe our definition was a little too narrow the other day. Because equivalent actually falls under consistent. Equivalent actually falls under consistent. What do I mean by DNE? Does not exist. Consistent solutions exist. They're going to be plural, lo siento, usually plural. We'll say exist. And then inconsistent solutions do not exist. Can all three planes be parallel? Sure, why not? Are there any intersections? Nope. What's the dilemma with this one, though? Like a little tent of cards sort of thing. Are there intersections? Yes or no? Yes, but can you guys tell from the picture? Why is it inconsistent? Why are there still no solutions? Clear intersections. Yeah. No, there's a hollow space in between. All three planes do not come together at all. How is that different from this one? All three planes intersect how? In an infinite line. So wait a minute. This one would be all solutions, except all solutions need to be on the plane. This one is going to be all solutions, but the struggle is only all solutions on the line where they all intersect, and then this one is one solution as in a point, an x and a y and a z. So hold on. What's going to happen to get this and get this in our math? And how do I express the answers? Because here's the struggle, guys. Is this all points as in all points as in all points? No, that's not a point. That's not a point. That's not a point. It's only points on the plane. So somehow it's restricted, but it's infinitely many. How are we going to show all but restricted? Same thing here. Is it all points? No. What about there, or there, or there, or there, or there? That's not intersecting. So they're going to be infinitely many, but not all as in all. In 2 dimensions, it was easy. In 1 dimension, it's going to be, in 3 dimensions, it's going to be a little bit harder. Here's the long story short, just to give you an idea. We are going to have equations for x and y and z in both of these. It's going to look a little weird. It's not going to be impossible. I'm going to show you how it works, but we're going to have equations for those solutions. If you guys want, you can grab a quick picture of it. I am going to change the screen. Some of you might want to play with the artistry of it later on tonight. Totally fine. Have fun with it. But in class, I can't allow you any more time. Grab a quick picture, but we're moving on. Consistent. There are solutions, but man, they can be different. Inconsistent. No solutions, and even that can be different. All the pictures, I think, have been taken. Oh, why is there? Oh, here we go. We're done. We're almost done. I've split this one. I've split this one into 7.3a and 7.3b. Here's the dealio. Homework due on Monday is both 43 and 44, but I've split it into 2. Why? Tonight, tackle A because you can do all of A, but I'm giving you weekend grace, so I'm going to have them both Google Classroom submitted on Monday. But I split them into 2 homework assignments. That way, you guys could know exactly what to do tonight. So 4.3a, totally doing tonight. 4.3b, and whatever you don't finish from 4.3a, finishing over the weekend. I know you're all packing up, but you shouldn't be, because don't we have one more example? Sorry, I have the number up here, but I don't have the actual problem. It got erased somewhere along the line. What chapter are we in? Oh, thank you. Not 7.4 yet, although that one's fun. I like 7.4 a lot, actually. Number 32. You guys ready? Adam, can you read it to me? 2x plus equals
1. And then 2x plus 6y plus 8z equals 3.
and then
6x plus 8y plus 18z equals 5.
you guys have just seen the system. Ready, set, go. Let's see if you can beat me. Doing the system. Doing the system. Yeah. Half minus 1/5 would be 5/10 minus 2/10. I wouldn't bet my life that I'm right, but I have a solution. Does anybody match my solution? Ooh. We're going to have to figure it out tomorrow. How can we double check? Ooh, how can we check our solutions with any of these, cool kids?